Vera Rubin telescope. For decades, we have gazed at the night sky and asked ourselves just how vast is the universe and what secrets lie hidden within its darkness. Now that veil is slowly lifting, clearer than ever before. Enter the Vera Rubin Observatory, the so-called all-seeing eye of the 21st century. Unlike Hubble or James Webb, which focus on a single patch of sky, Rubin scans the entire celestial sphere in just a few days, peering deep, wide, and fast like no telescope has ever done before. This is a historic leap for astronomy. Within its first 10 hours of testing, it discovered over 2,000 asteroids, including objects approaching Earth. It spotted dozens of cosmic lighthouses, RR Lyrae stars used to measure distances across the universe. And then the image known as the cosmic treasure emerged, revealing 10 million galaxies in a single frame. The astonishing part is that this is only 0.05% of what Rubin is expected to uncover. Equipped with a colossal 3.2 gigapixel camera and a nightly data stream of 20 terabytes, Rubin does more than capture images, it records history. This is the opening chapter in our journey to decode the rest of the universe, a place where darkness is no longer a mystery, but an invitation to explore. The journey to bring Rubin to life was bound by the most extreme physical challenges on Earth, where engineering had to confront the raw power of nature. The chosen location was the summit of Cerro Passion in the Chilean Andes, a site standing at 2,692 meters above sea level. This region is an astronomer's paradise. Its high altitude reduces atmospheric turbulence, the air is exceptionally thin and dry with minimal water vapor interfering with infrared observation, and the number of clear, cloudless nights is among the best in the world. Yet these ideal conditions created monumental logistical challenges. Constructing atop a steep, narrow, and winding mountain made transporting massive components extremely challenging. Huge components like mirrors and cameras had to be transported by specialized trucks, sometimes moving at a snail's pace, costing millions of dollars and taking weeks to reach the summit. Engineers and workers had to operate in low oxygen conditions with frequent high winds, strictly following safety and medical protocols, further increasing the complexity and cost of the project. To ensure Rubin could scan the entire sky in just 3 to 4 nights, engineers had to solve the problem of rapid precise motion. The high-speed optical system and mechanical mount were designed to move quickly, rotate 180 degrees, and stop with pinpoint accuracy within seconds, ready to capture the next target. This speed was critical, turning Rubin into a race-against-time astronomical machine. Finally, to protect the delicate and expensive equipment from the Andes' sudden weather swings, shifting from clear skies to snowstorms in moments, the protective dome could not be traditional. It was designed as a dynamic geometric dome capable of opening and closing in under a minute. All these factors combined transformed Rubin into a perfect fusion of immense physical scale and near-perfect technological precision. If building the Vera Rubin telescope was a decades-long battle against gravity and the harsh terrain of the Andes, then its operational performance is an instant declaration of speed and efficiency, officially ushering in the era of real-time astronomy. Even during preliminary testing nights with just 10 hours of observation, Rubin produced a volume of work and discoveries that traditional survey projects would take years to achieve. Rubin's core mission isn't just about taking images, it's about generating big data on the universe's ongoing changes. With every 15-second exposure, its gigapixel camera creates massive image files, presenting an unprecedented big data challenge. During full operation, Rubin is expected to collect and process over 20 terabytes of raw data per night. Algorithms must filter, compare, and classify this information almost instantaneously. Rubin's true power lies in comparing images of the same region taken minutes or hours apart to detect changes, that is, to capture transient events in the fleeting sky. Its combination of wide field of view and continuous capture speed allows Rubin to quickly track moving objects or variations in brightness across the cosmos. In just 10 hours of testing, impressive results were already evident, confirming Rubin's groundbreaking capability. For planetary defense, it detected 2,144 new asteroids, including 7 near-Earth objects. This instantly transformed Rubin into a real-time space surveillance tool, supplying the orbital data necessary for scientists to predict and warn of potential collisions with Earth, effectively serving as the ultimate early warning shield. Simultaneously, for galactic mapping, Rubin identified 46 RR Lyrae stars. These variable stars act as cosmic lighthouses, allowing astronomers to measure precise distances and construct detailed 3D maps of the Milky Way. More importantly, they help outline the boundaries and structure of the galactic halo, the region thought to harbor most of the dark matter. These numbers are the clearest evidence of Rubin's ability to capture the fleeting sky. It doesn't merely photograph static galaxies, it hunts for events. At full capacity, Rubin is expected to generate 10 million new event alerts per night, from supernovae and variable quasars to exotic new astrophysical phenomena. The speed of response is remarkable. This data must be processed and communicated to the global astronomy community within 60 seconds of capture. In short, Rubin's test night was not a display of beautiful images, it was the debut of a machine of time and speed. It heralds a new era where science no longer merely records what has already occurred but keeps pace with what is happening in the hidden darkness of the universe. The release of the first test images from the Vera Rubin telescope immediately redefined the scale and depth of astronomical surveys. At the heart of this attention-grabbing achievement is the massive mosaic image affectionately named by scientists as the cosmic treasure. Even as an initial trial, this image served as clear evidence of the unprecedented combination of wide-field vision and the instrument's fine detail capture capabilities. In a single shot, the cosmic treasure covered an astonishing 25 square degrees of sky, a field of view many times larger than any previous telescope. And within that expanse, it captured approximately 10 million galaxies. Remarkably, this staggering count represents only 0.05% of Rubin's ultimate goal. The Legacy Survey of Space and Time aims to catalogue 20 billion celestial objects over a decade. This expected data scale confirms that Rubin is not merely an observational tool, it is a cosmic data-generating machine, opening pathways to explore dark energy and dark matter in ways previously impossible. The depth of the image lies not only in the sheer number of objects but also in the way its colors reveal the history and distances of celestial bodies. Scientists analyze the image using spectral effects. The bright blue regions correspond to light from young, hot, luminous O and B-type stars, indicating galaxies in peak star formation stages and relatively nearby. In contrast, the deep red and faint streaks provide compelling evidence of the cosmological redshift. As light travels from the most distant galaxies toward Earth, the universe's continuous expansion stretches the wavelengths, shifting originally blue light toward the red end of the spectrum. These red streaks represent galaxies from billions of years ago, offering a direct and profound glimpse into the early universe, allowing cosmologists to test models of large-scale cosmic structure evolution. Particularly striking are the faint stellar bridges, the tidal tails connecting galaxies. These are unmistakable signatures of ongoing mergers and gravitational interactions, revealing how massive galaxies grow by assimilating smaller ones and how galaxy clusters form the largest cosmic structures. Rubin's most remarkable technical achievement is maintaining ultra-high resolution across this enormous field of view. The image enables viewers to perform a dramatic zoom, from a panoramic view of a colossal structure such as the Virgo cluster, gradually narrowing to individual galaxies, and finally resolving details down to 0.2 arcseconds per pixel. This absolute resolution represents a quantum leap beyond the capabilities of most ground-based telescopes. At 0.2 arcseconds, scientists can not only see galaxies but also analyze their internal structures at vast distances, distinguishing individual globular clusters, obscured star-forming regions, and intricate galactic morphology. The simultaneous capture of both macroscopic mass distribution and microscopic internal galactic physics with perfect consistency is the key that allows Rubin to open the door to entirely new frontiers in cosmic science. The success of the Vera Rubin telescope is not only due to its sheer scale but also lies in the integration of advanced optical, electronic, and data processing technologies, making it an unprecedented astronomical physics machine. At the heart of the system is the 3.2 gigapixel camera, a feat of engineering and the largest digital camera ever built for astronomy. This camera houses 189 deeply cooled CCD sensors to minimize noise, operating in unison to provide a 10 square degree field of view. To put this in perspective, that field of view can cover an area roughly 45 times the apparent size of the full moon as seen from Earth. Even more impressively, its resolution is held at an ultra-sharp 0.2 arcseconds per pixel. This combination of extreme wide-angle coverage and high resolution is key to Rubin's ability to repeatedly survey the entire southern sky in just a few nights, to read light and decode the history of galaxies. The camera is equipped with a system of 6 optical filters, U, G, R, I, Z, and Y. Finally, the project's greatest challenge lies in handling the enormous data flow it generates. With continuous scanning and imaging, Rubin is expected to produce roughly 20 terabytes of raw data per night, an amount that would take a typical user decades to generate. To process this volume, a dedicated data transmission network has been established. The data is compressed and transmitted at an astonishing 100 gigabits per second from Cerro Passion Observatory in Chile across the Atlantic Ocean to the main data processing center in Miami. This near-instantaneous transfer and processing capability is essential for enabling scientists to quickly detect transient events such as supernovae and near-Earth asteroids and to issue alerts to the global astronomy community within just 60 seconds of observation, turning Rubin into a cosmic time camera and an early warning system for the universe.